so that I can put it on our slides. And I am going to share my screen so we can all look at the same things. Okay, room number 1. This is Julia, Hayden, Chris, and Ruby. So patterns that you see, things you have in common, things you have that are different, I don't know, whatever you saw.
All right. We took the weight of 5 coffee filters, and across all our data, it came out to be 0.05 newtons.
Mm-hmm.
And since that was the weight, then it's equal. Since the weight is equal to the gravitational force, that means the gravitational force is 0.05 newtons.
Yeah, and then at like the end of the graph, you can see after around like 0.3 seconds, the line starts to get pretty straight. So that means that the drag force would be equal to the gravitational force. So then we concluded that the drag force would equal around 0.05 newtons after around 0.3 seconds.
Thank you. Hayden, Ruby, anything you want to add to that?
Pretty much, if since it's moving at a constant rate, the drag is equal to the gravitational pull.
Okay. We'll talk more about that in a second. Does anybody want to like refine that statement that the drag is the drag in fact equal to the, assuming you had a straight line, right? Is the drag in fact equal to the gravitational force?
I don't think so, because wouldn't it just be standing, wouldn't it just be floating in the air if that was true?
Oh, interesting. So would it not be falling? Oh, that's a great question. Okay, well, we'll talk more about that when we're doing this. So more like looking at your data. So what's going on over here? Like, what could you say about the motion right there?
The line was sort of like curving there, so the speed was like accelerating. So I think that means like the drag force might also be like increasing.
So you could say at least it's the coffee filters are accelerating, right? They're speeding up, right? And you can see that because you go from like a shallow angle to like a steeper angle, right? So that means it's going faster. And then I agree with you, at some point it looks like it's straight-ish. Okay, and then we can go from there. You measure things in seconds and in feet, you have labels, this is great. Group number 2.
So for the Vernier data, that tells us like if the coffee filters are going at a constant speed or not. And then if on the graph it like forms a linear line, then the speed is constant.
Okay. How did you manage to get a line that straight? More importantly, so that means like for the entire time, that was your data? For the entire time, it was like super straight like that? Or did you start videotaping after a while, or what happened?
I started taping immediately after, and then I stopped as soon as the point that I was measuring touched the ground.
Interesting. So there's no speeding up for you. It was always at that speed?
Yeah, and I dropped them flat, like flat as I could.
Got it. Okay. And you measured in pixels. Because you know what? Why not? Okay, and so you have a certain mass, and then I see your force diagram here. I can't. Okay, no, just like focus on the Vernier data. Okay, so it sounds like in your case, your speed was constant and it fell straight down. So it sounds like your velocity was constant, right? So not only was your speed constant, but your velocity was constant as well. Okay, room number 3. Ramsey, Marin, and Kian.
So we all had different amounts of coffee filters. So I know Ramsey used 10, I used 13.
Okay.
Or I think Marin used 10, sorry. But for this data, for 10 coffee filters, we got 0.125 newtons. And for my 13, we got 0.147 newtons or 15 grams.
Okay.
And similar to what the other groups have said in the like data from the veneer analysis,
Mhm.
the like blue line, the charts, it's like relatively this like a straight line, and the dots are evenly spread out, which shows that it has a constant velocity.
So first of all, this group, like your data is beautiful, like your data is really gorgeous. And I'm just going to push back just a little bit, man, just because, you know, do you really think that your data here shows that there's constant velocity?
Well, we were thinking that maybe like it's very close to constant velocity because it like has a slight curve, but it's not like a dramatic change.
What about here? Does this have a curve?
Well, I think maybe in our group, after a certain point, it got a constant velocity. So in the beginning, um, it was really clumped together because it wasn't falling. And then after a certain point, you notice that each point got closer and closer in distance. Well, not closer, but the distance between each point was the same as the next point.
So,
Yeah.
Darren, then do you want to, does that jive with what you observe on your data? Like, do you see that maybe after a while you get a constant velocity?
Yeah.
Right, like I would say, like here, I would argue, like, you're right. Here it's in a straight line, like that, right? The same way that for this one, here it's a straight line, like that. But like, this is a curve, yes? And that's a curve? Like, that is a curve, right? No? So what does a curve mean?
I mean, I guess it could mean increasing speed or decreasing speed.
Yeah, it's speeding up. Because it was sitting in your hand doing nothing, and eventually it's falling, right? So it's speeding up. But after a while, you're right, it is going at a constant velocity. Now, you did something interesting in this group. At least in your data, you showed us something interesting that the other two groups have not showed us, which was you seem to have two colors on your graphs, a blue and a red. You want to talk about that?
I think that's just like a setting in veneer analysis. Like you have to like take one of the like the red thing away because it's like unnecessary data.
Ooh.
Maybe it is necessary, but I think just like we didn't take it away.
Okay.
It's the X
And
and
by the
Y.
way, Maren, thank you for not taking it away because, you know, data is data is data. It's like, yeah, Hillary, you had your hand up.
I think it's the X and Y data. So the X is what we're kind of measuring the down vertically, and then the Y data or the X data we don't really need, which is just horizontally how is it moving.
So, right. So I'm gonna agree and disagree at the same time, Larry. That's my prerogative. So you're right that the blue data is measures up and down, right? Like vertically, what's happening vertically as the thing is falling, and then the red data measures right and left. I would argue it is actually this is the first group that can actually legitimately claim that their velocity is constant. Why? I would say for the other ones, their speed was constant, but I don't think their velocity was constant. Or at least I don't know that you can make that argument quite so cleanly. Kian, what do you think?
I think part of it has to do with the fact that it's dropping in a straight line, right? So, I mean, I know a lot of groups it kind of was like or it wasn't a perfect straight line, but our coffee filter drop within a straight line, and
Right? And how do you know it's a straight line?
displacement. So, and displacement is in a straight line. So yeah.
Because there's no motion in the x direction, right? So you see how that your red dots are essentially constant, meaning that whatever distance you were in the x direction horizontally, you're staying there, which means you're falling in a straight line. If you're falling in a straight line and your speed is constant, then your direction and your speed are constant, and that's a constant velocity. Everybody else, you only had one measurement, which was the y direction. And so maybe falling vertically, you had a constant speed, but I don't know that you had a constant velocity because I'm not sure what's happening. Did any of your coffee filters for all the other groups, did any of your coffee filters go back and forth like that, Isabel? Right? So the moment that happens, your velocity is not truly constant, right? Because it changes direction. Here, they actually have the data to show us that it does not change direction. Like it actually is a constant direction straight down. Hillary.
Maybe it has to do with the weight of the density, or I guess more like the mass of the coffee filters.
Right. So we can, so we can talk about how to make sure that that happens. But do you guys see that it is, so first of all, Maren was right. It is something that you can change in Vernier. You can include the red dots or not include the red dots. You should totally include the red dots, right? Because those are the only things that can guarantee that you're going in a straight direction. Like if your blue dots show like a straight line and your red dots are a straight line, then that means that your velocity is constant. Otherwise, it's not really clear, right? So make sure that like it's not a figment of your imagination. It's actually really important. Okay, room number 4. What do we see?
We had like some miscommunications or like difficulties with some of the collecting of the data, but so we found that after I think most of us dropped it from 4 feet, and so the first like 3 feet, at least for mine, they weren't really falling constantly, but then for like the last foot, it started to fall at a more constant speed, and I do not have the red dots because I knew that mine wasn't falling in a straight line based on when I was plotting it on the picture.
Okay.
So.
Okay. Okay. Oh yeah, Hillary, Lowell, anything you want to add?
Well, we found that the weight of 5 coffee filters, this is, I think, Isabel, with the spring scale, it measured at 0.13 newtons. So that could obviously tell us or help tell us like the weight and more. So yeah.
Okay.
Yeah, and also both the y and the x direction, or both y and x fluctuated in velocity, and it's especially apparent on my data there with the this like kind of bump in the middle of the curve,
right?
Because of it kind of twisting and falling like a leaf.
Got it. Yeah. So like right here, like the bump right there. Yeah. Cool. Okay, room 5.
Okay, so like, so I couldn't like convert my thing, like part of my thing from pixels to like meters per second. So we couldn't fully compare our data, but for like ours was pretty inconsistent. So I think we're gonna do like retry it because like mine at like 0.8 seconds was like like 46 meters, and Tate at 0.4 seconds was about 45 meters. So like we find out that that was like pretty inconsistent. So we might have to like do like a retrial kind of thing.
Yeah, I'm just going to say that. So you can include the blue and the red dots in your position time graphs, or you can include the motion map, right? And you can look at the motion map and you can see that when it's on motion map, you can see the thing is falling straight down, right? It's not going like wink, 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 wink like that. It's going straight down. So that's a constant, that would be that's a constant direction. And then you have a nice constant speed here at the bottom, right? So that's constant direction, constant speed. That's a constant velocity. We'll work on the pixels. Okay, so how do we improve? So we've seen everybody's data, right? How do we improve what we have? Like, how do we make sure this is what you have today, right? You have till next week to write your paper. So what do we need to improve our data? Like, collectively, what do we need to work on? Yeah, Hayden.
Making sure it's really falling at a constant velocity instead of just vertically.
Right. So how are we going to do that? What data do you need to show that that's
the red dots?
Right, you need both the X and the Y direction. I would also include the motion map, right? Like the dots on the movie, like that would also tell you whether or not you're going in a straight line, right? So I would include the motion map as well as the position time graphs, and I would do a position time graph for both the X and the Y direction. Now, let's assume that you see a little bit of going back and forth. What are some options to make sure that disappears? What are some things that we can tweak? Isabel?
Drop it from higher and with more filters.
More filters. Nobody says you all have to have the same number of filters, right? If you drop more filters, there's more like it's going to be heavier and it's just going to fall down better. So if you have more filters, use more filters, right? It'll help you get a more straight trajectory, okay? And then you can drop it from higher up because you see how like, even for example, for this one, you see that at the end here, it is, oops, that is not what I wanted to show, what the heck? What just happened? At the end here, okay, I'm just going to, at the end, you have this line seems like it's going in a constant line, but we'd like to have it longer so you can guarantee, right? So anyway, it would be nice, what just happened? So it would be nice to have more data points. So make it go from higher up,